This is the last section in this trigonometry class. Yay! So we're still in chapter 6 where we're talking about analytic geometry, and section 6.7 is called plane curves and parametric equations. So the first objective is going to be to graph parametric equations by hand. The second one is to use a graphing utility. And we're not going to do that one, but we are going to find a rectangular equation. So that's with x and y, a rectangular equation for a curve defined parametrically. And then we're going to skip using time as a parameter. I'll talk about that, but we're not going to do anything with it formally. And then the last objective we are going to do is to find parametric equations for curves defined by rectangular equations. Okay, so you already know that a graph is a collection of points in the xy plane, and that collection of points is called a plane curve. So remember that a collection of points can look like anything. It can look like dots, it can look smooth, it can look like an ellipse. There's lots of different kinds of shapes that are called plane curves. So we have seen a plane curve represented as a function f of x. Then we've also seen a plane curve that was an equation of a conic section. So now we're going to talk about another way of representing a plane curve that incorporates additional information. So it's really useful in areas of science, say, where things are changing, particularly with respect to time. So you often will see t used as the parameter, and I find it really helpful to think of it as time. So we're going to let x equal some function of t. So as t changes, x is changing in a particular way. And then we're going to let y be some other function, g of t. So as t steps along, y has different values according to the function g of t. So f and g are two functions who have a common domain, some interval I, and then the collection of points defined by points x comma y that are f of t comma g of t, that's called a plane curve. And these equations are called parametric equations of the curve. And the variable t is called a parameter. And we're not going to talk about this a lot, but this can also be a theta. So that's how it's kind of connected to what we're doing in trigonometry. So the first thing we're going to do is graph parametric equations by hand. And this way of representing a plane curve is especially useful for describing movement along a path. So if your plane curve is going some kind of path, but maybe you have a particle that's going slower, and then it's going faster, and then it's going slower, the parametric equations can describe that movement in a way that the static graph of just y equals f of x can't. So suppose we have a curve defined by these parametric equations. X equals some f of t and y equals some g of t for t in a particular range of values between a and b. So for any particular value of t, we can find x, which equals f of t, and y, which equals g of t. And so we're going to make a three-way chart similar to the xy chart or the r theta chart, but now it's going to have t, x, and y. So for any particular value of t, we can find the x and find the y, which gives us the coordinates of a point, x comma y, on the curve corresponding to that value of t. Now t can either be discrete values like 0, then 1, then 2, then 3, or it can be continuous. It just depends on what it is that you're trying to represent. So as t varies or changes, marches along, we can find more points that are on the curve. And in fact, we can see that the curve is traced out in a certain direction as t increases. So the other thing you can tell is the particle traveling this way or this way by how the curve is parameterized. So there's lots of different ways to parameterize a given curve, and we'll talk more about that towards the end of the section. So the specified values of t give us beginning and ending points of the curve, and they also specify the direction or orientation of travel. Are you going clockwise around a circle? Or are you going counterclockwise? So we can imagine a particle traveling along the path, and if we choose evenly spaced values for t, we can actually get information about the speed of the particle along the path. So when you put a in for t, where this a is the beginning of the interval, then x, which equals f of a, y, which equals g of a, this is going to give you the beginning point of your travel. And then when you get down to b, and you have the x coordinate is going to be f of b, and the y coordinate is going to be g of b, then that's going to be your ending point. So it's a way of saying I only want this piece of the curve if I only go from A to B. Okay, so here's some exercises. We're supposed to graph the curve whose parametric equations are given and show its orientation, and then find the rectangular equation of the curve, and then verify using a graphing utility. So let's make a little table with x is going to be square root of 2t, y coordinates are going to be 4t, and our values of t are supposed to be greater than or equal to 0. So we're starting at 0, where x is 0 and y is 0. So 0, 0, the origin, that's the first point on our graph. So here's the point 0, 0. Okay, then let's pick some easy values for t. So let's pick t as 2. So then we get x is 2 and y is 8. So the point 2, 8, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8 is a point on this curve. Okay, so then the next one that would be easy would be, say, 9/2. So if I do t is 9/2, then I get x is 3 and y is 18. So 3, 18 is a point on this graph. So we don't know exactly what the shape looks like yet, but let's see if we can figure that part out. So we do know that we start here at the origin, and then we're going in this direction. So let's see if we can figure out what the curve looks like. So the way you can do that is by solving one of the variables for the t and plugging it in to the other variable. So if I square both sides of the x term, I get that x squared is 2t. So then t is x squared over 2. And then I put that in where the y is, in for the t. I get 4x squared over 2, so I get y equals 2x squared, which we know is a parabola. So it's a parabola that keeps on going, but we only are getting the right half of the parabola because of the way it's parameterized and with the t being positive only. So you only get one side of the parabola in this way. Okay, so the next objective is to find a rectangular. So we're going to find a rectangular equation for a curve defined parametrically, which is basically what we just did, finding the rectangular equation of the curve. So we do this by eliminating the parameter. Sometimes it's easier than other times. So this example is pretty simple. Of x minus 4 is the square root of t. So then you can plug in x minus 4 here instead of square root of t and get y equals x minus 8. So you can see that this is going to be a line. And then let's make a little chart. With t and x and y. When I start with t is 0, oh, this graph isn't going to start at the origin. When t is 0, x is 4 and y is negative 4. So the point 4, negative 4 is the first point that we want on this graph. So 4, negative 4. So here's the first point when t is 0. So this is the start. Okay, then let's pick easy values again. So when t is 1, I'm going to get x is 5 and y is negative 3. Okay, then let's pick t is 4. And I'm going to get x is 6 and y is negative 2. And then let's pick 9 and get x is 7 and y is negative 1, and we can see that this is a straight line. You can tell what direction you're traveling as t increases, so you put little arrows on the path to indicate that. Okay, and then we'll do some of these harder ones together in class. And then the last thing we're going to do is find parametric equations for curves defined by rectangular equations. And this is actually pretty easy. If you just say, well, let me let x equal t, well, then y is going to be negative 8t plus 3. So we can see that this is a line, and this is just a parametric description of the line. One parametric description of the line, but there's more than one way to do this. So you could have y equal t, and then t would be negative 8x plus 3. So then you'd have t minus 3 over negative 8 would be the x. So this is another set of parametric equations that would also draw the same curve, but let's talk in class about what will be different then.